Hi, this is Erin O'Neill. For lab 2, I found the velocity of the moving balls by using the values given, which were in these columns, which were in, in these columns. Yes, that's a column. Which were given. So to find, for example, the velocity of object A, I set it up as an equation where it equaled the change in x over the change in time. And so how I plugged it in was I found the difference in position between these last two cells over this period of time, which is 0.005, so 5 milliseconds. And I dragged that down, so as you can see, each of them reflect this. And so I did that for object A, B, and C. And so dragging them down after 1.25 seconds, I got their final velocities, but I only needed it really until it had moved over 1 meter because the slope was 1,000 millimeters. So I highlighted that here. So this was object A, and its related velocity at that distance over this much time had gotten it to a total velocity of 2.52 meters per second. And then the same is true with object C. It's kind of in between these two numbers, but its final velocity at the end of a meter was 2.31 roughly, so you can see it's kind of between these two. And yeah, I plotted those. This is the position versus time graph, and then this is the velocity over time, which the slope of this shows the acceleration, so you can see they're all constant accelerations, and that the object B goes the fastest, A goes the second fastest, and C goes the slowest, which makes sense here because object B is the puck, which is hollow and it's not rolling, and then the next fastest is the baseball, which is also supposedly not hollow, even though I'm pretty sure baseballs are slightly hollow, but in this equation it's not hollow. And then the racquetball's the smallest, and it's also hollow, and then move the slowest down the ramp. Okay, so that is my Excel work, and then I'll show you this guy. So problems 5 and 7, use the x versus t to find the acceleration of the ramp. So, okay, I guess I'll go back to the Excel to show that. So what I did was I found the average slope of each of these. So like I said, the slope gives you the acceleration. And so by finding the slope from like this as it relates to this time, oops, I don't want to do that. So here you can see I found what the x was in relation to y, and I just carried this down. So it summed for the entire, all the values. And I did it for B versus the time and C versus the time. And that's how I found these answers. I hope that's a good enough explanation. If not, let me know what you'd like to hear more about next time. I'm just a little unsure, but okay. As in, I'm a little unsure what exactly you want me to say, but I think that covers it. Okay, and then number 7. So my hand calculations to find the acceleration. What I did was first I set it up for the baseball, knowing the translational kinetic energy and rotational kinetic energy, and equaled these equations. Let me get it in this view. And so basically the only thing that was different for them was their mass their moment of inertia, and their radius. I think that's all that I was solving for at that point. And so I knew the moment of inertia for the baseball was 2/5 mr squared. And so when I plugged that in, I could actually go through and cancel out, you know, the r's and the m's. And I ended up with the Fs. So the Fs equals 2/5 m times acceleration. So I could plug this number, this equation back in. Let's see, where did I plug this guy back in? Well, oh, right, sorry. Okay, so I plugged it back in for the translational rotation, or the translational kinetic energy. Up at the top, you see mg sine theta minus fs equals mac mx. So where this fs is, I plugged in this equation. So doing that, I could cancel out the m's. I moved over the 2/5 ACM, added it to this side, and ended up with a equation of the acceleration equals 5/7 times gravity times the sine of theta. And I'd already solved for theta. I knew theta was 27 degrees. So when I plugged in these numbers, which I already had for everything, I got the solid sphere, which is the baseball, rolled with an acceleration of 3.18 meters per second by the bottom of the ramp. And so I applied the same kind of formula for the hollow sphere of the racquetball. So knowing that I was 2/3 mr squared, I plugged this in for the friction. I'm forgetting the exact terminology for the friction coefficient or something. And so I knew that was 2/3 m times acceleration. So when I plugged that into this translational kinetic energy equation, I ended up with acceleration equaling 3/5 of gravity times sine theta. And so plugging in my numbers there, I found the acceleration for the racquetball as 2.67 meters a second. And since the puck wasn't rotating, it was slipping because there was no friction, I could just go through and plug it in through this equation, which is more simple. And so solving for the acceleration of it, I just got 4.45 meters per second squared. And that all checks out when I look at these figures, these values in this, they're the same thing, which is awesome. So very happy to see that. And then, yeah, I think that's all I have to explain. So, yes, lessons learned is basically save my work really carefully because I lost my Excel documents multiple times. For some reason, they wouldn't save the graph, and I had to keep going back and redoing it and like re-entering these calculations. Like the numbers were there, but the equations weren't. So I don't know what I was doing wrong, but I redid this Excel thing multiple times. I want to save it right now. Okay, so 9 minutes later, there you go. That's the recap.